The next presentation is a science highlight by Callum Anderson. And he'll be talking about exploring local scale flow structure in thermospheric winds using a bistatic array of all-sky imaging Fabry-Perot spectrometers.
Okay, so this morning I'm going to be talking about thermospheric wind imaging, mostly neutral winds at F-region altitudes. And I'm going to be focusing in particular on some of the new results that are being made possible by combining two all-sky imaging Fabry-Perot spectrometers to form a bistatic array. So some of the people involved with this work are Mark Conde, Geophysical Institute, who designed and built the instruments and has a hand in everything to do with them. Jeff McCarg at the US Air Force Academy, he owns one of the instruments that I'll be talking about. Mike Nichols, who is our contact for the Poke Flat AMISR. So our motivation, what we want to do is to try and understand how thermospheric wind structures evolve in response to the dynamic forces associated with the auroral ionosphere. And to do that, we seek to produce high resolution, two-dimensional, that is horizontal wind maps for a given altitude. So our instruments, as I said before, are all-sky imaging Fabry-Perot spectrometers. These are sometimes called scanning Doppler images, and that's how I'll refer to them, SDIs. So these instruments record upwards of 100 airglow spectra from multiple locations across the sky simultaneously. From each of those airglow spectra, we can derive line-of-sight wind speed. And so these instruments are really ideally suited to neutral wind imaging. From a single instrument, we can derive a two-dimensional vector wind map from the spatial variation of the line-of-sight wind. However, doing this requires some fairly big assumptions about the underlying wind field. When you have two of these instruments nearby, such that their fields of view overlap, then in the region of overlap, we can use the information from both instruments to uniquely resolve two of the three vector wind components. And this requires fewer assumptions than the monostatic technique does. So the move to bistatic imaging is really important for a couple of reasons. Firstly, it gives us an independent means of deriving wind maps. So we can take these bistatically derived wind maps and compare them with monostatic wind maps that we've been deriving for years and see just how good or bad the assumptions underlying those monostatic wind maps are. Secondly, and more importantly, because the bistatic wind measurement involves far fewer assumptions about the underlying wind field, and the assumptions that we do need really don't make much of a difference to our results, we can probe the wind fields at much smaller spatial scales than we can with the monostatic technique. So bistatic imaging is really a local vector measurement of the wind, which is very good. So I'm just going to briefly go through the monostatic and bistatic fitting techniques. I'm just going to highlight the most important parts. This image over here is meant to show what the SDI sees. So these colours represent Doppler shift across the sky. So blue shift means the wind's moving towards the station. Red shift shows the wind moving away. And what we want to do is turn this variation of line-of-sight wind into a wind map, as shown by the arrows. So to do that, we first of all we approximate the wind field by a first-order Taylor expansion about the zenith. So we're already making some big assumptions about how the wind varies spatially. So what we get is a Taylor expansion in each of the zonal and meridional wind components. And we actually need one further constraint in order to fit that model, and that is we need a constraint on one of the partial derivatives or one of the gradient terms in the Taylor expansion. So the one we choose is we assume that the zonal gradient of the meridional wind is 0. Now, we have good assumptions for good reasons for believing that that gradient should be, on average, most of the time, smaller than the others, but the assumption that it's equal to 0 we know is really not correct, and it's a pretty bad assumption. But it turns out that if you go away and calculate this gradient using the bistatic wind technique, and then you feed that gradient back into the monostatic wind fit and you see what difference it makes to the wind fields, it turns out it really doesn't make a big difference to the overall picture that you get from these monostatic wind fields. So even though it's a bad assumption and we know it, we can tolerate it because it really doesn't affect our results too strongly. So that's the monostatic technique. Bistatic technique is when we have two interferometers nearby and their fields of view overlap in some region. The region of overlap we call a common volume region. And in that common volume region, we get two independent samples of the same nominal wind vector. Importantly, we get that along two different lines of sight. And so we can invert those measurements to give us uniquely 2 of the 3 vector wind components in the common volume region. In order to project that onto the horizontal, we do actually need to make an assumption, and the assumption that we need is we need a value for the local vertical wind. Now, for simplicity, we just set the vertical wind to be 0. There are other options you can choose, but it turns out that that assumption is really doesn't affect our results too strongly for a couple of reasons. Firstly, thermospheric vertical winds are quite small, frequently less than 30 metres per second in magnitude, and they average very close to 0. Secondly, we can actually choose our biostatic geometry to minimise the impact of that assumption, as I'll show you shortly. So biostatic wind inversion is a local vector measurement of the wind, and it's really much more direct than the monostatic technique can give us. So the 2 instruments that we've been using are Poker Flat and at the HARP facility down at Gakona. I'll refer to that as either HARP or Gakona probably. Poker Flat is in orange here and HARP is in blue. Each of these sectors represents a location where we get a line of sight wind measurement. So there's 115 of these sectors for each instrument. So for the biostatic technique, we want to know whereabouts those zones overlap. So if for example, we pick all the ones with which overlap by more than 10% of their areas, we get this subset of zones, which results in these biostatic locations. All these green squares here represent a location where we could, in theory, do a biostatic wind inversion. Now, as I said before, we want to try and minimise the impact of that vertical wind assumption. And so what that means for us is that we pick zones that are sufficiently what we call off-zenith. And all that really means is that we remove a strip of biostatic locations along the line joining the 2 instruments. So in what follows, these are going to be the locations where we're going to do our biostatic wind inversions. And for reference, geographic north is straight up there, and magnetic north is 23 degrees clockwise. So now for some results. A natural first question to ask is, well, just how well do the 2 independently derived monostatic wind fields from both instruments agree, since they're both sort of independent estimates of the wind field. So here we show some data from the January 24th, 2010 of the wind fields, and we've sort of put it in the context of the global scale circulation, global scale thermospheric circulation. So the blue arrows here are the monostatic wind fields derived from Gakona, or HARP. The orange ones are the ones derived from Poker Flat, and these have been subsampled to reduce the number of arrows there. We've actually got higher resolution available than this. And the white arrows are 1993 horizontal wind model winds to give us the global circulation. And in the background behind these arrows, you're going to see some green colours coming and going. That's an all-sky image recorded by the Poker Flat SDI. So I'll play this through and I'll pause it when we get to something interesting. The first thing we're going to see is a line of shear developing as the aurora comes down from the north. Pause that there. So the first thing, well, a couple of things jump out. Firstly, the 2 monostatic estimates agree pretty well. They both turn around at the same time. They both show the strong westward flow to the north. They show some eastward flow to the south. And so this tells us that the assumptions underlying the monostatic technique really, they can't be too terrible. The other thing you notice is that the observed winds are approximately perpendicular to the model winds there. This is not too surprising. HWM is a large-scale empirical model. It doesn't really have the spatial resolution or the resolution in its geophysical inputs to be able to capture the sort of forcing that's associated with this auroral arc here. So we're not too surprised that they don't agree, but it sort of does point out the need to actually go and measure the wind, if you want to figure out what's going on. So I'll let this play through. You'll see that the agreement stays pretty good. The shear starts to dissipate. The field becomes more ordered. There's some curvature in the flow there. Coming through at about magnetic midnight here with some anti-sunward flow coming down the page. And now we see that the measured and model winds are in pretty good agreement now. And as we get into the dawn side, you start to see some westward flow again. And the model's sort of rotating to catch up here. So the agreement's not too bad now that the sort of the local forcing has been stopped. So 2 things from that. One, it's important to measure the wind because we can observe structures that at least models like HWM can't capture. And secondly, the 2 monostatic wind fields, independent estimates of the same wind field, agree pretty well. And so that tells us something about the assumptions underlying the monostatic wind field. So now we want to compare, we want to see what the biostatic winds look like on this night. So same night of data, we've zoomed into the Alaska region here and we've done away with HWM. The red arrows there are the biostatic wind vectors. They'll be popping in and out of the movie because the biostatic wind technique is more sensitive to the underlying data than the monostatic wind field is, so we have to be a bit more careful with our data selection. I'll play this one through. And you'll see the same sort of story. The agreement, again, between the biostatic and the monostatic is pretty good. They show the same strong westward flow coming through there as the line of shear moves southward. Occasionally you see some odd vectors. But overall the agreement is pretty good, and you would say that both the biostatic and the monostatic are showing, telling basically the same story here. Now towards the, as we get into dawn here, we're going to start to see a little bit of disagreement in the monostatic wind fields. I'll pause it when we get to that. Particularly sort of up north here, the monostatic winds aren't in agreement between the two stations, whereas down the bottom here, basically they're telling the same story. Now, we believe that that's because there are some structures in the wind field that the monostatic technique just can't capture because of its underlying assumptions. And it's in those cases and at those times that biostatic imaging or local vector imaging is really the one you want. That's the one you're going to take to the bank. I'll let that play through. So that's the horizontal winds. Another really big advantage to having a biostatic array is that along the line joining the two stations, here we've got Poker Flat and Kokona. This is the great circle between them. If you do biostatic imaging at points along that line, one of the two wind components that you measure is the vertical wind. And so this allows us to actually map out the vertical wind along that line. So if we go and do that, starting off at the Poker Flat zenith, we've got vertical wind. And as we move down common volume 1, we're moving down this line in latitude over here. And so these are the vertical winds in each of the common volume regions until we get down to Kokona zenith. The scale there is minus 40 to 40. Most of these winds are between minus 20 and plus 20 metres per second, so they're rather small. I'm not going to go into the details of that, but just the fact that we can actually resolve the spatial variation of the vertical wind, even if it's just along one dimension, is really a big step forward. There's really nothing comparable to this in the literature at the moment. And we have only the vaguest notions of how horizontal spatial scales of vertical winds how they behave. And so this sort of data gives us, important tools to be able to investigate those topics. So this is a sort of important new science. I'll skip through that one. So the neutral winds, of course, depend heavily on what's going on in the ionosphere. The two ions and neutrals are strongly coupled. And co-located with the Poker Flat SDI is the Poker Flat Advanced Modular Incoherent Scatter Radar, FISA, which you've been hearing about. FISA is able to sample along multiple beams simultaneously, so it has a similar capability to the SDI in that regard. And these two instruments combined are sort of ideally suited to imaging local scale neutral and ion flows. So we recently completed a campaign of coordinated SDI and FISA observations. That ended on April 5th of this year. That was initiated by Mike Koch at Lancaster University. So for what I'm going to show on the next slide, maybe just focus on this panel on the right here. These blue squares indicate the locations where we're going to have a FISA-derived ion flow vector, and this is the Poker Flat SDI look directions as before. So I'll show you some data from that campaign. This is from April 5th, the last day of that campaign. What we've done is we've just averaged the two monostatic wind fields from both Harp and Poker just to reduce the number of colours we've got on the plot here. So that's the average monostatic is in white arrows there. The red arrows are the the SDI biostatic winds, and FISA is going to be in blue there. I'll play that through. So you'll see that both the ions and the neutrals are flying in basically the same direction, basically flying west up here. Some aurora will come through there, and the magnitude of the ions will increase westward as the neutrals sort of turn southward. And I'll play that through again. There's a period there where, and I'll flick through it, where the neutrals turn sort of southward and the ions turn to follow, but then they turn back again. So I'm sort of flicking through that now. So here we turn southward and then the ions go back. So they respond sort of in lockstep for a bit there, and then the ions go back to doing their own thing. So this, this is very preliminary work, and we haven't really analysed this stuff in detail, but this allows us to look at ion-neutral coupling sort of really quite directly. We can plot, we can take averages of the wind vectors, both ion and neutral, and we can see how they respond to each other, which ones lead the other. During this campaign, we actually had data at 2 altitudes, so we had E and F region, and so we can see what differences, if any, there are at the 2 altitudes. So looking ahead, there are actually a couple more SDI instruments currently being built at the Geophysical Institute, and they're planning on being deployed at Tulik Lake and Kaktovik up north. So with the addition of the new instruments, obviously we'll have a whole lot more places where we can do biostatic imaging. These are the locations where we'll be able to do biostatic imaging, these black crosses here. As you can see, we've greatly increased our coverage. But more importantly, when you start to get 3 or more instruments, you can begin to do tristatic wind imaging. So tristatic wind imaging means that you get all 3 wind components without any assumptions. And so if tristatic is good, then if biostatic is good, then tristatic is better. And these are the locations where we expect we'll be able to do tristatic imaging. The density of the point on here is probably slightly optimistic, but even if it was 50% of that, we would still have very good coverage for tristatic imaging. And for example, we'd be able to greatly extend our ability to do vertical wind mapping, for example. So this is, exciting new possibilities there. So I'll sum up. Monostatic wind imaging, we found, it's a reliable technique. It works under a large range of conditions, and the structures that we've been seeing all this time really are there in most circumstances. However, sometimes there's just too much structure in the wind field, and the monostatic technique can't capture it. And so in those cases, we need direct local vector measurements of the wind. And so in those cases, biostatic or tristatic, if you've got it, are really essential. So the biostatic array, as I mentioned, not only allows us to resolve horizontal winds at better spatial resolution, but we can also begin to start to map out the spatial variation of the vertical wind, which is really new. As we get more instruments, we can start to do tristatic imaging, and we also increase our coverage, as I mentioned. And when we combine the SDIs with the capability of instruments such as FISA, we can begin to examine the neutral and ion flows on a range of scales and maybe start to identify the extent to which these scales are coupled, which is some exciting new research. That's a lot. Thank you.
Thanks, Callum. Some nice new results.